All right, we are approaching the end of this module, and in this unit we're going to discuss how to implement the VM translator on the Hack platform. And this is indeed a turning point in this module, because up until now I did not commit myself to the Hack platform, and I described in very general terms how to implement our VM, our virtual machine on any given computer platform. So now I'm going to make a commitment to a certain target platform, which will be the Hack computer. So I have to give you some information on how to do it. So let us begin with the big picture, which is extremely important. And the picture is that we begin with some Jack program, presumably. And the Jack program is stored as one or more Jack files, which are put in a certain directory, or you may call it folder. And this directory has a name. I call it myprog. And then I'm going to apply the Jack compiler to this entire directory. And the Jack compiler is going to create in this example, two new files, which will be the VM translations of the Jack files. So one will be called, by default, foo.vm, and the other one is going to be called bar.vm. And every method, constructor, and function in the source code is going to be translated into a VM function in the target code. Now, this process is something that you don't have to worry about, because we're going to discuss it at length later on in the course when we build the compiler. But from now on is certainly our business, because now we are in the world of the VM, and we have to translate this code further. That's what the VM translator is all about. And the VM translator is going to do something dramatic. It's going to take all these different standalone functions and kind of weave them into, well, weave is not a good word, but it will transform them into a single assembly file. So notice how several things got lost in the translation. When we translated from Jack to the VM, we lost the notion of constructors, methods, and functions, because everything became functions. And when we translated from the VM to assembly, we lost the notion of functions, because now we just have a long stream of assembly commands, and we have to use assembly in order to capture the semantics of the source VM code. So this VM translator is actually the program that we are developing in the current project and in the previous one. So that's the big picture, and we are going to write the assembly code on the right-hand side using Hack assembly, because I made this decision that I'm going to implement it on the Hack platform. And in order to do it, I have to comply to certain conventions. And the first convention is booting. You know, what should I do when I turn on the computer? How will the computer know to execute my program? So here are the assumptions that I request to make. First of all, there should be a VM programming convention. And the convention is that one file in any VM program must be named main.vm, and one VM function within this file must be named main. Okay, so this is something that the compiler has to take care of, because the compiler is going to write this VM code, and it's going to be taken care of, quote unquote, automatically, because we have the same requirement at the Jack level, right? You will see that when we write Jack programs, we also require that at least one class will be named main, and one function in this class should be named main also. So this convention we're going to get it for free, quote unquote. All right, then we need a certain convention in the implementation, in our case in the VM translator, When the VM translator, when the VM implementation starts running or is reset, it has to start executing an argumentless operating system function called sys.init. So the VM implementation must begin with this code. It must call sysinit, and sysinit is already programmed at the OS level, which is not our business right now. So sysinit is already programmed to call main.main and enter an infinite loop. So sysinit, once it starts running, will end up causing the programmer's program to start running as well. The main.main will start running, and then the whole Tetris game or whatever it is will start executing in front of us. Finally, we need some hardware platform convention to comply to, and that is what is known as the bootstrap code. Okay, we have to somehow call sysinit, so the sysinit will be able to call main. And so we request that the code that you see here will be stored in the computers, in the target computer's instruction memory, beginning in address 0. Because the computer that we built, the hack computer, is programmed to start executing the program which is stored in the instruction memory, beginning with address 0. That's one of the operational rules of the hack computer. And not only hack, most computers in the world comply to this convention here. So the first thing that the computer will do is it will set SP to 256. And by doing this, it will determine that the stack should begin in this address in the host RAM. And then it will call sysinit. These two things must be done in machine language, in assembly. And that's it. And from this point onward, let the show begin. Everything will roll smoothly because the VM translator will know what to do with every VM command. That's what we did in the last, in all the units actually in this module. All right, now in order to generate code that complies to all the explanations that I gave before, we have to propose some standard mapping on the hack platform. I explained in the previous module why we need a standard mapping, and indeed, if you recall, this is just a summary of everything that we did so far. We use the hack RAM, and we use it to store all the pointers that you see here using the scheme here. I'm not going to explain it because we went through it in detail throughout the units. But now I also want you to see this thing in the overall context of the host RAM. So this is the entire host RAM of the hack computer. It consists of about 32,000 words, and the top 2K words are what we've been discussing all the time. That's the blue stuff on the left. And then we have several other areas on the host RAM, which we call heap, memory mapped I/O, and some unused space. And as far as the VM implementation is concerned, we worry only about the top 2K of the RAM, and everything else is something that is going to be used for other purposes. Purposes that are not within the jurisdiction of the VM implementation. So we'll move on to the last slide in this unit, and that is a documentation of all the special symbols that your VM translator ought to use. So first of all, in the previous module, we decided to use these special symbols. And I'm not going to repeat this information now. And in order to implement everything that I described in this module, we are going to use a few more conventions that you see here. We're going to use 3 more types of special symbols for generating labels. And what I have here is just a screenshot from the book that accompanies this course. You're welcome to read this information on your own. I'm not going to dwell on it because it's very technical and not extremely interesting. So now it's on you to write the VM translator and generate all the code which is necessary in order to implement the VM language. And in the next unit, we'll describe how to actually do it using an implementation language like Java or Python in which you will write your VM translator.